Hi everybody, this is Mrs. Ellsworth, and today we're going to be talking about how to calculate the different mechanical advantages again, but we're going to go through your worksheet. You had a yellow one handed to you before we left the building, and this one is just simply in simple machines. There is another formula in there that you're going to have to learn too. It's on efficiency. I couldn't get that far with that other video, and let's get started. Anyway, so we're going to be talking about ideal and actual mechanical advantage. And so every single one of those formulas that they did on the mechanical advantage of those simple machines, on the individual 6 simple machines, those are all the ideal mechanical advantage. So that's what would happen, what we think would happen if it was in a frictionless type of situation, but that's not true. Okay, and sometimes gravity also deals with a little bit more too. They're very close, but they are never ever 100% efficient. Nothing ever is. Anyway, so in a couple cases we'll calculate the efficiency, and I'll show you how to do that in this video too. And so, let's go ahead and get started. So the ideal mechanical advantage is what you've been learning in all these different videos that we've been talking about it. And so the ideal mechanical advantage for a, I would just call it MA, for a lever, goodness. Okay, it is going to be the length of your effort over the length of your resistance. So what is our resistance? And I told you also in the video that resistance is usually a weight that you're using, or it is what you're applying the force to. And but quite often it's just the weight, the resistance weight that you're pushing around. In this case right here, the length of the resistance is going to be from the fulcrum to the middle of this weight, and I believe it says on this sheet right here, I think it says on 1 meter. So there we go. So the length of the resistance will just be 1 meter, and then the length of the effort, that's where you're pushing it from. Okay, and it is also where it's a force is being applied. You'll often see in any type of word problems to see applied force, effort force, or where you're pushing from. Anyway, so that'd be from here to there, so that's going to be 3 meters. And so the meters cancel out, and so it's just going to be 3. So the mechanical advantage, the ideal mechanical advantage, if there's no friction or anything like that going on here, is going to be 3. Now the actual mechanical advantage is that other formula that you guys talked about, and this is where you're always going to see forces. Okay, and this is always the force of the resistance over the force of the effort. This could also be used in any type of problem like how much a forklift lifts, or any type of other machine where you see forces. All the other problems will have lengths in them. This is the only one that you got forces. So the actual mechanical advantage, I don't know why I didn't go and put that on there. The actual mechanical advantage, it is actually, is forces. All the others are lengths. Okay, so in this case right here, a force of our resistance, well, it read as 128 newtons. So 128 newtons. Okay, and then the force of our effort is going to be 55 newtons. Okay, again, these are newtons, and they will cancel out. Don't know why I have a box there. It's bothering me. Well, anyway. Now I got an eraser on here. Okay, so when you go and take 128 and divide by 55, you get 2.3, and it keeps on repeating. So 2.3, and again, that is your mechanical advantage. This would actually what would come out of the machine when you're actually doing it. So notice that it is not real efficient there. I mean, it's pretty efficient, but there's something going on there. Probably a lot of friction going on. Anyway, so to calculate the efficiency is actually going to be the AMA. Okay, so that's what you actually got out of the machine and what you actually ideally thought that you would get. So, and that makes sense because it'll never be over 100% ever. Okay, if they are telling you that they got some kind of machine that's 100% efficient or else greater than 100% efficient, they're pulling your leg. Do not spend your money on it. Anyway, so you have to also times this by 100. And when I did that, I got 77%. Oh boy, that barely fits in there. 77%. Okay, moving on. Okay, most of these other problems, if they've got newtons in them, then of course you're going to use that other MA formula that had newtons in them, that had forces in them. And that's why in the video I didn't know if I should put an AMA there or an IMA. I wasn't sure what to do there, so I just put them all as MA, the way that I learned it years ago. But anyway, so here we've got a mechanical advantage of a machine that lifts, okay, 100 Newton weight. So that is our resistance, isn't it? Okay, with an effort force, effort. So here's effort force of that. So we know that the mechanical advantage of this, okay, is going to be the force of the effort over the force of the resistance. The force of the resistance is 100 newtons. The force of the effort is 20 newtons. So it's going to be 100 over 20. And so then our answer then will be, where am I at here? 5. This can be 5 times easier to use this machine than to not use it. Okay? Notice that this one's got newtons also, and you can finish solving that one. It'll be with the same exact formula. Sorry. Anyway, with this, let's look at this one right here, number 3. What is the mechanical advantage of an inclined plane ramp that is 12 meters long and 0.8 meters high? So you can tell that on this one right here that we would have 0.8 meters high, okay, and we would have it 12 meters long. And in this case right here, you would have 12 meters. Okay, so let me write out the formula. So this is the ideal mechanical advantage again, too. All of them will be the ideal mechanical advantage again, unless they have the newtons written down. And so this is length over height. Okay, and the length in this case is 12 meters over 0.8 meters. And when you go and divide that, you should get 15 for an answer. So it is 15 times easier to go and use this ramp than it is for you to walk over and carry it and put it up over it. Now, that may not seem like that big of a deal, but unless you have something that is as big as like a piano, you'll understand why it is a whole lot easier to do ramp than to not. I had a player piano that had a broken player inside of it, and so it was very heavy. It had lots of brass in it. It was very, very heavy, and there's no way that those college athletes could have ever helped me do it without a ramp. Okay, there's another ramp. Okay, pulley. What is the ideal mechanical advantage of this pulley? If you remember right from the video that we are talking about, oh dear, hang on. We are talking about how many parts the string is attached, or how many times is the string divided by a pulley that's there. So this one is going to have the mechanical advantage of 2. Okay, and so it's 2 times easier using this. And it's kind of crazy because when you do start pulling up on D, you will see how much easier it is. With these movable pulleys, it does make it twice as easier. So what is the spring scale going to read? Well, what would you do? You go and take your weight and you go divide by the mechanical advantage, your ideal mechanical advantage. Okay, same thing. I don't know where call every single one of those ideal mechanical advantages or else just mechanical advantages. Anyway, so we've got the weight, which is 200 newtons, and we're going to divide it by 2. So end up having 100 newtons for your for what's going to read on that spring scale. I don't know why I keep on getting those weird squares on here. You'll notice at the bottom of this that there are some block and tackles, and so you'll follow along with them from what you learned about the strings in your video and solve them that way too. And then you can take the weight divided by your mechanical advantage, your ideal mechanical advantage, and get how much that would read. When we do these in class, students are always amazed by how much easier that it makes your effort from these block and tackles. And then they always fall apart too, so they were troublesome too. Okay, just wanted to tell you number 7 is just like our number 1, but lots of students miss this because it's kind of hidden. Don't forget you've got to still do this one right here where you've got to figure out the ideal mechanical advantage of this lever. Here is your weight, by the way, and then calculate your efficiency. I don't have much for efficiency on this worksheet, and that's okay because we have a very shortened quarter here. Okay, what is the AMA of an inclined plane? You know how to do that. The MA of a lever with a weight placed 1.5 feet from the fulcrum and the force. Let's just draw this one out. What is the MA of a lever? Okay, with a weight placed 1.5 feet from the fulcrum. So what would that look like? Well, I think here, let's go ahead and some might think, well, gee, Mrs. Ellsworth, how do you know? How do you know if this is a first-class lever or if it is a different one? Okay, if you've got your weight placed right here, it is 1.5 meters from the fulcrum. Okay, so it's 1.5. Okay, and that is your weight. Okay, and then over here we'd have that our effort then is being applied at 3 feet. That's fine too. So if you would go and even think about, well, what if the fulcrum is down here? Okay, and we're pulling up at 3 meters. And I've got our mass set right here at 1.5. I'm sorry, they're not meters, they're feet. Okay, anyway, so if that's the case, you're still going to have the same exact mechanical advantage. So just recognize that this right here is your force of your resistance, and this one is the force of your effort because it's being applied, so it's your effort. And you can go ahead and finish solving that one. You know that levers is just the force of the effort over the force of your resistance. Okay. Those again are more levers. Okay, here's an ideal. What is the mechanical advantage of a fixed pulley lifting a can of paint, 330 newtons? Well, the mechanical advantage of a fixed pulley, you might remember what it is, but let's say we don't. In this case, here's our paint, is 30 newtons. How much are you going to have to pull over here? 30. So you go and you take your length of your effort. Excuse me. It's like a lever now. So it really wouldn't be any different than length of effort over length of resistance, and then you'd end up finding that it's 1, which is the mechanical advantage of a fixed pulley. So that was kind of a trick question, and I was trying to make some sense out of it too. If you ever go online and you watch Bill Nye, he'll talk about how that wheel and axles are like levers, and sometimes fixed pulleys are too. Okay, there's one last one on here that I wanted to talk about. Okay, and sometimes students will get this one because it's a two-part question. Okay, what is the resistance force? So that's what we're looking for. We are looking for what is the resistance force. So force of resistance is what we're looking for. So we are going to lift a lever with 3 meters of resistance, with a 3-meter resistance arm. So that's the length of our resistance. Boy, that's not easy for me to see tonight. Okay, and when we lift a 24 Newton force, so that's going to be the force is newtons is force of our effort, and then we're applying that to a effort arm. Okay, so that's the length of your effort. Okay, well, I will tell you something on this, that what you can do is that you can do your length of your effort over length of your resistance, and you can get an MA. Okay, it doesn't matter if it's ideal, which is the formula for ideal, or not. Okay, they're talking about this situation where that the MA still also equals the force of your resistance over the force of your effort. And so when you really think about that, you've got something going on here. You could go and just realize that you've got two proportions equal to each other and just get rid of that MA. Otherwise, you can go ahead and calculate the MA first, And then you can then later on put your thumb over this side, okay, and then you could see that the MA, you'd have that calculated. You'd also have your effort force calculated, so you could find your resistance force. So you could do that a couple of different ways. Okay,